Have you ever looked up at the night sky, gazing at the endless tapestry of stars above you, and felt a sense of wonder about what lies beyond our world? Have you ever wondered what it would be like to actually visit those distant stars, to leave Earth behind and set out on a journey across the cosmos? Imagine if you could travel at the speed of light, nearly 300,000 kilometers per second, faster than anything we've ever built, fast enough to circle the Earth more than 7 times in a single second. This isn't just science fiction. It's a concept that's fascinated physicists, dreamers, and storytellers for over a century, ever since Einstein first described the strange rules of relativity. Traveling at this unimaginable speed would change everything you know about time and space, warping your experience of reality itself. The rules of reality would bend in astonishing ways, making the familiar seem utterly alien. The tick-tock of a clock, the distances between places, even your view out the window, all would transform, stretching and compressing as you race through the universe. This journey challenges our common sense and reveals just how strange and mind-bending the universe truly is. So, let's embark on this thought experiment together, imagining ourselves as cosmic travelers on the ultimate adventure. We're not just crunching numbers, we're exploring what it would feel like to break the boundaries of time and space. Would this speed let you peek into the future, or see the universe in a way no human ever has? Could you conquer time itself, or would you discover new mysteries waiting in the fabric of space? The journey begins with a simple question. What does it truly mean to travel at the speed of light, and how would it change your place in the cosmos? Buckle up, our exploration of time, space, and the future is about to begin. The universe is waiting, and the adventure starts now. The speed of light is the universe's ultimate speed limit. Nothing can go faster, no matter how hard we try. It's a fundamental rule woven into the very fabric of reality, shaping everything from the tiniest particles to the largest galaxies. Light, radio waves, and all information travel at this exact speed, nearly 300,000 kilometers per second. That's about 186,000 miles per second, a number so huge it's almost impossible to truly grasp. It's so fast, it's hard to imagine, enough to circle Earth 7 times in a single second. If you could travel at light speed, you'd reach the moon in just over a second. Scientists call this speed c, and it's constant for everyone, no matter how they're moving or where they are in the universe. This constancy is one of the most surprising discoveries in all of physics. If you're in a car and turn on your headlights, both you and someone on the street measure the light at c. It doesn't matter if you're moving toward or away from the light, it's always the same. This is the cornerstone of Einstein's theories, and it completely changed how we think about space and time. The speed of light isn't just about photons, it's a rule that shapes the entire universe, influencing how cause and effect work and how information can move. It sets the boundary for what's possible and connects space and time, weaving them together into a single fabric we call space-time. When we look at distant stars, we're seeing them as they were years ago, because their light has taken so long to reach us. The universe doesn't do instant messaging. Light always takes time to travel. So we're always peering into the past when we look into the night sky. Understanding c is the first step to understanding the bizarre effects on time and space, like time slowing down or distances shrinking as you approach light speed. When you push against this cosmic speed limit, the universe pushes back in strange ways, warping reality itself and revealing the true weirdness of our cosmos. And that's where things get truly interesting. Because the speed of light isn't just a number, it's the key to unlocking the mysteries of the universe. What happens to time when you travel close to the speed of light? It's one of the strangest questions in all of physics, and the answer is even stranger than you might expect. Time itself slows down for you, a phenomenon called time dilation, predicted by Einstein's theory of relativity. For the astronaut speeding through space, time passes more slowly than for everyone back on Earth, even though it feels completely normal to them. Your watch ticks slower, your heart beats slower, and you age slower. To people on Earth you seem to be moving in slow motion, but to you, nothing feels different. But to you, everything feels normal. Your thoughts, your actions, and your heartbeat all seem unchanged. Imagine a clock that uses a beam of light bouncing between 2 mirrors. This simple device helps us visualize how time changes at high speeds. On Earth, the light travels a short, straight path between the mirrors, ticking off time at a regular pace. But on a fast-moving ship, The mirrors are moving too, so the light travels a longer diagonal path between each tick. Since the speed of light is always constant, it takes longer for each tick to happen. So, your clock runs slow compared to clocks on Earth. The closer you get to light speed, the more extreme this effect becomes. Time stretches out, and the difference grows. At 99% of light speed, a single year for you could mean 7 years have passed on Earth. Your friends and family would age much faster than you. At 99%, a year for you could be 70 years on Earth. The world you return to would be almost unrecognizable. Scientists have tested this with atomic clocks, on planes and satellites. Even at our everyday speeds, the effect is real, though tiny, proving time is not absolute. Time isn't universal, it's flexible and personal, shaped by how fast you move and where you are in the universe. For the light-speed traveler, time becomes elastic, stretching and bending in ways that challenge our everyday understanding of reality. As time slows down, space does something just as strange. It shrinks. This is called length contraction. For the astronaut, the universe in the direction of travel appears squashed. The distance to your destination physically shrinks from your perspective. A 10-light-year journey at 99% of light speed might seem only 1.4 light-years long to you. That's why you could make the trip in just over a year, while people on Earth see you gone for 10. Time dilation and length contraction are two sides of the same coin. Without length contraction, the universe would be uncrossably vast. With it, a journey across the galaxy could fit within a human lifetime for the traveler, while millennia pass outside. The universe rearranges itself around your motion. Time and space aren't absolute, they depend on how you move. This is the heart of Einstein's special relativity. The traveler's reality is just as real as anyone else's. Traveling near light speed lets you leap into Earth's future. You could leave in 2025, travel for 5 years, and return in 2525. You've become a time traveler, jumping forward in time. But can you see the future as you travel? The answer is no. Information, including light, can't travel faster than see. To see an event, the light from it must reach your eyes. At near light speed, you're outrunning the information from Earth. It's like speeding away from ripples in a pond. You never see them. You travel into the future, but you do so blindly. You'll only learn what happened when you return and slow down. You're not watching the future unfold, you're skipping ahead. When you arrive, you find yourself in a new chapter, surprised by what you see. The future remains a mystery until you're actually in it. Let's make this real with the twin paradox. Two twins. Stella boards a spaceship, Terra stays on Earth. Stella travels to a star 20 light-years away at 99.5% of light speed and returns. For Terra, the round trip takes just over 40 years. She's 70 when Stella returns. For Stella, time passes 10 times slower. She experiences only 4 years. She returns barely older, while Terra has lived a lifetime. Both experiences are correct from their own perspectives. Stella didn't watch Terra's life unfold. She simply skipped it. She left at 30, returned at Terra's 70th birthday, with only 4 years passing for her. This isn't a contradiction. It's relativity in action. The future is a destination, not a spectacle. You can travel to the future, but you can't preview it. That's the fundamental difference. What would you see from your lightspeed ship? The view would be spectacular and bizarre. Stars ahead crowd together, their light blue-shifted and brilliant. Behind you, stars spread out and fade, their light red-shifted and dim. At extreme speeds, stars behind vanish into infrared and radio waves. You'd fly into a tunnel of blue-shifted starlight, with darkness behind. The brightness ahead could become overwhelming, even dangerous. The cosmic microwave background would blue-shift into deadly gamma rays. Without shielding, this radiation would be lethal. The universe enforces its speed limit with harsh consequences. Your perception of the cosmos is shaped by your motion. Colors, positions, and brightness are all relative. For the light-speed traveler, the universe becomes alien and awe-inspiring. It's a reminder of how limited our everyday perception really is. Can we actually reach the speed of light? For anything with mass, the answer is no. As you speed up, your effective mass increases. Near light speed, your mass approaches infinity. To reach c would require infinite energy, impossible in our universe. The speed of light is a horizon you can approach but never cross. Only massless particles like photons travel at light speed. For a photon, time doesn't pass at all, its journey is instantaneous. At light speed, time stops completely. This is a state massive objects can never achieve. The barrier isn't just engineering, it's a fundamental law. We can imagine wormholes or warp drives, but these are speculative. For now, we're bound by this ultimate speed limit. The universe lets us get close, but never all the way. So, can we see the future by traveling at light speed? The answer is no. Physics prevents information from arriving before it's created. The future remains a closed book, until you arrive in it. But you can travel to the future by moving fast enough. Time slows for you, letting you leap across centuries while aging little. This is a direct consequence of relativity proven by experiment. Time is not rigid or universal, it's personal and relative. Your journey through time is shaped by your journey through space. The faster you move, the slower you age. Understanding this connection deepens our appreciation of existence. Imagining these journeys expands our horizons. The universe is stranger than we can imagine. The future we can travel to is a powerful reminder of the cosmos we inhabit.